Algebra 1 students, welcome back from your Christmas vacation. Hopefully you all had a wonderful break, and we are going to get going with Chapter 6 with our notes today. Alright, so we're going to take a look at systems of equations. Systems of equations are two or more linear equations that use the same variables. The solution of a system of linear equations are any ordered pair that makes all of the equations in the system true. All right, and so we're going to take a look at what that means later on. Examples of when systems of equations might be used are listed here with a couple of sentences or a couple of scenarios where you would compare the distance and speed, and you could almost kind of leave the rest of this sentence out, but you could compare the distance of speed and distance of anything. In this particular case, we're looking at two different cars, and we're going to see when one car might catch up to the other car. The other types or the other examples of when systems might be used, you could kind of do the same thing where you define your variables and then you kind of just leave a ... but we'll take a look at the entire situation. It says compare pricing plans of phone companies to see which is a better deal. You could also compare the growth rates of different types of plants or animals to see when they might be the same height or same weight. So you could really compare pricing, or you could compare growth rates of different types of fill in the blank, whatever you want. So that's kind of my point there. And for number 6, or for number 1, excuse me, for chapter 6, I'm going to have you go ahead and pause right now and read this problem to yourself. Okay, welcome back. It says, suppose one puppy weighs 5 pounds at birth and grows at a rate of 0.25 pounds per month over the first several months. Another puppy weighs 4 pounds at birth and grows at a rate of 0.5 pounds per month. After how many months will the puppies weigh the same amount? So this is asking us to write the equations. And when I write the equations, I'm going to take a look. Most times when I'm attacking these word problems, I want to look at this very last sentence. It says, after how many months will the puppies weigh the same amount? So I know, based on looking at that, that my x variable is going to be my time in months, and my y variable is going to be my weight. All right, so my equations will look like this. Y is equal to 0.25x plus 5. Okay, I've got a puppy that grows at 0.25 pounds per month, and he starts at 5 pounds. All right, my next equation is going to look like this. My puppy is going to grow at a rate of 0.5 pounds per month, and he's going to start out at 4 pounds. Okay, now I want you guys to pause the video and write the steps, or write step 2 down, because you can handle that. Good review for you. All right, hopefully you paused your video and actually did your work on your own, and hopefully you understand that 0.25 is the same as a quarter, which is the same as 1 divided by 4, which is the fraction I have written. I did the same thing for the second equation for the second puppy. So there's your answers. Let's move on to the next slide, and we can actually solve by graphing. All right, so here's what I want you to do. I want you guys to do step 3 on your own. You're capable of it. That's what we did in chapters 4 and 5, and then we're going to come back together and talk about step 4. All right, folks, welcome back. Hopefully you paused your video and graphed your lines on your own. If not, we're going to blow it. We're going to give you the answer because it's already written down. However, you can't just use that point that I have indicated, or that ordered pair that I have indicated right there, because the question asks you how many months, or after how many months will the puppies weigh the same. So if you wanted to, you could write a sentence that said something like, after 4 months, the puppies, we actually know what they're going to weigh. They're going to weigh 6 pounds. So you could make a statement like that, and you would be correct. And we're going to move on. All right, let's talk about how to classify your systems of equations. I am going to open up my little laser pointer here and talk about the different lines. So I'm going to talk about this red line right here. If I was talking about only this red line right here, and I was asking you what the solution of what the solution of that red line would be, you could say any point across that entire line and you would be accurate. However, when we're dealing with systems of equations, we have this entire other line here that we have to deal with as well. We've got this blue line, and I honestly can't tell if that's blue or purple. You guys can make fun of my ability to see color later. But when we're talking about systems of equations and we have exactly one solution, we're going to have a situation like this, which is the most common, where your two lines are going to intersect somewhere at this point right here, and that is going to be the answer to your system of equations. And so if they intersect at one point, that is said to be consistent because there's an answer or there is a solution to your system of equations. And since they intersect at one point, you can think about that as being independent. There's just one of them. So that's the way I remember it. And so we're going to take a look at this other situation. So we've got a red line, and we've got this blue line right on top of it. We actually have two parallel lines that have the exact same solution. So in that particular case, we would say that there are infinitely many solutions. The lines are the same. They are graphed right on top of each other. And so that is said to be consistent because there is an answer. You can plug in the same y values and same x values into either equation, and you're going to get the correct answer. It's going to satisfy the solution. And it is said to be dependent. It is dependent upon one another to be everything across that line. And then we have this case right here where we have two parallel lines. I've got this red line and this blue line that are completely parallel to each other. This is said to be inconsistent because you are not going to find a solution to that system of equations. And if we remember from our previous section, we know when we're going to have this situation without graphing it. We're going to be talking about in this particular section graphing it, but in the other sections we're not going to be graphing it. And you're going to know that they are inconsistent or that there is no solution because you can see when you start to solve some of these system of equations whether or not you're dealing with a slope that is exactly the same. So that's how we define or classify. That's how we classify our systems. All right, I kind of spent a lot of time fumbling around with how to say what is described here in this graphic organizer for you on the last slide. So I've given it to you here in your notes, and I'm going to move on for the interest of time. All right, we're going to solve this system by graphing. So I noticed that these are in standard form. I'm going to go ahead and switch them into slope-intercept form. It's a little more useful for graphing. So I'm going to add 4x to both sides of my first equation here. And I'm going to end up with negative y is equal to 4x minus 1. And then I'm going to go ahead and divide both sides by a negative 1. And I'll have y is equal to a negative 4x plus 1. And I had to do that to get rid of that negative in front of the y there. That's why I divided both sides by that negative 1. Okay, so I'm going to take this other one and I'm going to change it into slope-intercept form. I'm going to add 2x to both sides using the addition property of equality. So I've got y is equal to 2x minus 5. Then I can go ahead and graph both of these linear functions. So I'm going to have a y-intercept on that first one of positive 1. My slope is negative 4, so I'm going to go down 4 and to the right 1. 1, 2, 3, 4, and to the right 1. Okay. So that is going to be 1, 2, 3, 4, and to the left 1. Okay, and I could make some more points across there if I wanted to, but I'm going to go ahead and draw my line there. Roll with that. My next one's going to be at negative 5, so 1, 2, 3, 4, 5. And my slope is positive 2, so I would go up 2 spots and to the right 1 spot. And what do you know? That's going to be this point right here. So I can go ahead and graph that line. And my solution would be 1, comma, let's see, 1, 2, 3, that's a negative 3. So that would be the solution to that system of equations. Alright, so on this one, what I want you to do is pause your video. Go ahead and set up both of your graphs, and then we're going to come back together to talk about the part of this, the instructions where it says tell whether the system has one solution, infinitely many solutions, or no solution. Okay, so go ahead and pause your video and do your lines on your own. Okay, so here are my two lines. They don't look perfect, but I think you can get the picture. What I did was basically used the slope-intercept form of the equation of the line for the first point to graph it. So I had a y-intercept of negative 1, and I had a slope of 2. I did the same thing. I just had to divide by 3 on both sides for the second equation, and I got this funny little fraction here, and I know that you guys like to freak out when you find a fraction, but anyhow, what we have is two parallel lines. If you analyze just the slope of your two lines, you would notice that we have a situation where we have parallel lines. So we actually have this situation going on right here. There is no solution. These two lines would continue on into infinity in both directions, and they would never ever cross each other. So you're never ever going to find a solution to this system of equations. Alright, just like the last problem, I would like you guys to go ahead and pause the video, graph your lines. We'll come back together and talk about whether or not it has one solution or infinitely many solutions or no solution. So go ahead and graph your lines and pause the video. Alright folks, welcome back. Hopefully you paused your video and figured out that you have two lines. They're right on top of each other. They occupy the exact same space. That is the situation right here where there is an infinite amount of solutions. So if you want to write your little infinity sign and say infinitely many, that is fine. Or you could write out infinitely many solutions. Either way is totally fine. And folks, that is the end of your notes for 6.1. Come to class ready to work hard.